Well, aloha everyone. Today we're going to talk about the magnetic force on charged particles. So here is what we are talking about. Charged particles both create magnetic fields. Remember, moving charged particles create magnetic fields. But charged particles will also feel magnetic fields. They're also affected by magnetic fields. So if you take a charged particle and you drop it into an external magnetic field, that charged particle will feel a force. And in fact, the magnetic force on a charged particle, so remember, B is magnetic field, so FB is the magnetic force, that's going to be equal to, and it's a vector, so don't forget, it's going to be QV cross B, where V and B are vectors. All right, so here is what is going on in this formula. And you might have seen this as B times Q times V or something like that, but the correct way is QV cross B. So this obviously is magnetic force. Over here, Q is the charge of the particle. So if we talk about an electron, that's the charge of an electron. If we talk about a proton, it's the charge of a proton. If we talk about a 1 coulomb charge, it's 1 coulomb. All right, then we have V. You'll notice that this is a velocity V. And you'll notice I put little serifs on it to make it look faster so that we don't confuse it with a voltage V, which will be showing up in some of these things. So yeah, that's a V for velocity there. And then B, if you have a hard time remembering that, just remember, you put a wing on the back of your car. It doesn't actually go any faster, but it looks faster. Same thing with the V. We put the wings on the V. It looks faster, even though it actually isn't. And then we have B. B is going to be the magnetic field. And remember, the magnetic field has a direction, so it's a vector. So how do we apply this equation? Well, the first thing that we do is we need to draw a diagram of whatever our situation is. So let's imagine we have a charged positive particle right here. Maybe it's maybe it's a proton. Yeah, let's make that a proton. So we have a proton that is right here. The first thing you need to notice here, we'll put this in a magnetic field, and the magnetic field will be directed. Let's direct the magnetic field into the page. So this entire area has a magnetic field that is directed into the page, like so. It's a uniform magnetic field, so it's the same strength everywhere. Pretend I drew those X's nice in a nice regular pattern to show that it's the same everywhere. Okay, so something like that. All right, so the first thing you need to realize is that magnetic fields affect only moving particles. If this velocity is 0, the force will be 0. And that proton will sit there forever because objects at rest stay at rest. So it turns out this magnetic field is not going to affect this proton unless we make it start moving. So let's say we start moving our proton to the right. That's its velocity. Now our proton is moving. Maybe it's going to go, I don't know, how about 1,000 meters per second? So here goes our proton. It's traveling to the right. It's moving 1,000 meters per second. We also know that our magnetic field here, B, let's make it a magnetic field of 0.1 teslas. And we will be asked, what is the force on the proton? And I want to know both magnitude and direction. Well, since this is a nice 90-degree type thing going on here, we can use the cheater way. We can use, to find a cross product, the first vector times the second vector times the sine of the angle between them. So we can use that to find the cross product, and we can use the right-hand rule in order to figure out the direction. So let's start by figuring out direction, because that's actually the harder part of this. So the first thing we're going to do is we're going to look back at this formula, and we see that it is Q, V cross B. So the cross product is between V and B, velocity and magnetic field. So we're going to take our index finger and we're going to point it in the direction of the velocity, which to me is to the right. That's probably reversed on your video, but that's all right. So velocity is this way, and the magnetic field is into the page. So I need to move my hand around until my middle finger points into the page, which is something like this for me. When I do this, you can see my thumb is pointing toward the top of the page. So what is my direction going to be? The direction is toward the top of the page. Now, if this was, well, if I could spell here, toward the top of the page. If this was an electron instead of a proton, if it was negative, that negative would have showed up on the charge, which means that the direction of the force would have been flipped. Instead of going toward the top of the page, it would have been toward the bottom of the page. But since this is a proton, we'll stick with the positive, and that way, and toward the top of the page. Okay, now that you have this, we can figure out the magnitude of the force. Because remember, we can do this by using the cheater way of doing a cross product, which is the first vector times the second vector times the sine of the angle between them. So FB is going to be equal to Q. So the Q just comes down, and then V times B times the sine of the angle between them. And that's a velocity V. Okay, cool. So this is equal to my Q, my charge, is a proton. A proton's charge is 1.6 times 10 to the negative 19th coulombs. Times my velocity was 1,000 meters per second. Times my magnetic field is 0.1 Teslas. And times the sine of the angle between the magnetic field and the velocity. Actually, the velocity and magnetic field that way, right? Order matters. So which way is the velocity? To the right. Which way is the magnetic field? Into the page. So what's the angle between those? Well, that's 90 degrees. So it's the sine of 90 degrees. We already know the sine of 90 degrees is going to be a 1, so we don't need to worry about that. And this is going to be... It's going to be 1.6. I can see that already. This is 1 times 10 to the 3. This is 1 times 10 to the negative 1. So this is negative 19 plus 3 is 18, 17, 16. And then minus 1 is negative 17. So times 10 to the negative 17. And my units, it's a force. So it must be in newtons. I'm not going to go through the thing to prove that to you. Just take my word for it. Or prove it to yourself. So 1.6 times 10 to the negative 17th newtons is going to be the force on this proton. This demonstration shows what happens when electrons are interacting with magnetic fields. But in order to see it well, we're going to have to go lights out. So after a couple seconds, the camera adjusts here, and we can see down at the bottom there's this kind of purple haziness. But then up here you can see a thin beam where electrons are hitting a phosphorescent plate. So this plate is coated with phosphorus, and when the electrons strike it, they will leave a beam of light. I'm now going to take a magnet, and I'm going to bring it close to the tube. And as I move it closer, you will notice that the beam begins to deflect. As I move it away, it moves back to normal. That curving of the beam is due to the magnetic force that is exerted on these electrons. If I use the other side, the opposite type of magnetic field, you can see that this causes the beam to go the other way, and it deflects it more. Flipping back around, you can see that the beam deflects to the right. Flipping to the other side, the beam deflects to the left. Even though the magnetic field is either directed into the phosphorescent plate or out of the phosphorescent plate. So in the video that we just saw, you can see that electrons are flying up from the bottom, going this way with a certain velocity, E minus. There we go. So there's electrons flying that way. And the magnetic field can be either directed into the tube, which in my drawing is into the page, or when I flip it around, it can be directed out of the page. So this is one possible magnetic field arrangement. And then the other possible magnetic field arrangement is going to be the same sort of thing, except, well, here's our electron going this way. But instead, the magnetic field is directed out of the page. So when I take my magnet and I turn it around, the magnetic field is directed out of the page instead of into the page. Okay, so here is our diagram. In the first situation here, we have a velocity that is directed toward the top of the page. We have a magnetic field directed into the page, which means it should feel a force to the left. However, this is an electron, which means its charge is negative, which means the force is in exactly the opposite direction. So the force on this electron is going to be directed to the right. What does that mean? The electron is going to curve that way. When we have this other type of thing going on, we have velocity this way, magnetic field out of the page, which means it should be directed toward the right. But since it's an electron, it gets directed toward the left, and we can see that it's going to get deflected toward the left. So the math on these things is not that hard. The hardest part about this is understanding that right-hand rule. And it's a good thing we talked about vectors and cross products before. So get to know that right-hand rule, get familiar with it. Once you're good at that, really, that's the hardest part about talking about magnetic forces on moving charged particles. So that's really all there is to it. Mahalo for watching, and see you next time.